Dear teacher, this is our presentation of assignment calculus 2B. Our topic is design the most coefficient beverage can, which is concerning partial derivatives and optimization. Then my name is CST Wenxiao Zhou and my student ID is CST2509044. This is our presentation roadmap. As you can see, we divided into 6 parts. The real-world problem part, calculus concepts, mathematical model, work example, interpret results, and the practical implication. Then let's start. First, the real-world problem. Cans produced annually worldwide, which is about 118 billions. That's about 5,700 cans every second. The standard, like the 355 milliliter can, is everywhere, vending machines, supermarkets, fridge, and so on. So it seems fine, but we must consider is it mathematically optimal. But why cost matters? We list 3 factors. The first factor, material, aluminum. A typical can uses 13 to 15 grams of aluminum. Material alone dominates production cost. And then second factor is shipping handling. Can ship affects how many feet in a shipping container. If it's taller or if it's wider, that really changes packing efficiency. The last one is price volatility. Aluminum hit $3,800 per ton in 2022. When prices spike, even 100% saving per can becomes critical. So we come to a core question. In some scenario, it's really wasteful if a can uses just 500% material than necessary, but in globally lies millions of tons of excess aluminum, so it's wasted. Then we consider opportunity. Even a 100 reduction in material per can save the industry billions of dollars over time. So our goal is to use calculus 2B to find the mathematically optimal dimensions that minimize cost while containing fixed value. And we see a beverage can as a cylinder, so we use the formula to calculate its value equals to pi r squared h in the series, which is contain 3 parts, the top bottom surface and the lateral side area. So S is equal to 2 pi r squared plus 2 pi r h. Then my friend will continue the part. Thank you.
Hello, my name is Ye Jianqing, CST2509054. And let me introduce the concepts first. First one is partial derivatives. Since the cost depends on both the radius and height, partial derivatives help us understand how each variable affects the cost. And second is constraint optimization. The volume of the can is fixed at 355 milliliter, so the radius and height cannot change freely. We use the volume equation to connect these 2 variables. And finally, we use the critical point in second derivatives test. We find the critical point by setting the derivative equals to 0. Then use the second derivative to confirm that it gives the minimum cost. So let's build the mathematical model first. First, we write the volume constraint. V equals to pi r squared h equals to 355 milliliter. It is a constant. And then we express the height as V divided by pi r squared. Next, this constraint let us eliminate one variable later. Next, we build the cost function. Since the cost depends only on the amount of aluminum used, it is proportional to the total surface area of use of the can. So the surface area includes the top and bottom plus the curved side. So the cost function is this. And finally, we substitute the h. by the equation we get. So the cost function is this. So it is a single variable function, and it is much more easier for us to optimize. And then we can have understanding the cost about the cost function. The first term represents the cost of the top and the bottom. As the radius increases, the cost increases, so the circular area becomes larger. And the second term represents the cost of the side surface. As the radius increases, the height decreases, so the part becomes smaller. And these two terms work against each other. They compete each other. A small radius makes the cane tall and increases the side cost, while the larger radius increases the top and bottom cost. Therefore, there is an optimal radius where the total cost is minimized. So in the next part, we will use the differentiation to find the optimal value. That's all for my part. Thank you very much.
Hello, I'm Yin Pei-Shen, CST 2509055. Now I will explain how we find the optimal dimensions of the beverage can. In the previous section, we built the mathematical model and obtained the cost function. Our goal is to minimize the material cost while keeping the volume fixed at 355. First, we differentiate the cost function with respect to the radius r. The derivative tells us how the cost changes when the radius changes. This is an important step because it helps us find the point where the cost is the lowest. Next, we set the first derivative equal to 0, and the minimum point, the slope of the function, is 0. So this allows us to find the optimal solution. Then we substitute the volume of 355 into the equation. After taking the cube root, we find that the optimal radius is 3.84. Next, we substitute this value back into the volume equation to calculate the height. The optimal height is 7.68. And the most important result is that h equals to r. This means the height is exactly equal to the diameter of the can. Under our assumptions, this is the most cost-effective design because it minimizes the amount of the material used. And now let's look at the results. For standard 355 beverage can, the optimal radius is 3.84 and the optimal height is 7.68. The root of h divided by 2r is equal to 1, which confirms our conclusion that the height equals to the diameter. Next, we verify our solution by using the second derivative. Since the second derivative is positive, so the critical point is a minimum point instead of a maximum point. Therefore, we can confirm that our solution is mathematically correct. And finally, we can compare our result with a real beverage can. We can see that a real can is usually taller and has a smaller radius than our design. This is because real companies consider more than just a material cost. They also need to consider transportation, customer comfort, project appearance, and marking. These practical factors affect the final design of the can. And therefore, our mathematical model provides a theoretical optimum, where real beverage cans are designed to balance both the cost and the practical requirements. So this is all of my part. Next, our speaker will explain the practical applications and the limitations of this model.
Hello, my name is Chen Letian, CST 2509002. Our optimization result is h equals 2r, which means the height is equal to the diameter. This gives the best balance between the top and bottom area and the side area. If the can is too wide, more material is needed for the ends. If it is too tall, more material is needed for the side. So h equals 2r minimize the material cost. However, real beverage cans are not designed only by mathematics. Engineers must also consider internal pressure, consumer performance, shipping efficiency, and manufacturing costs. Because of these factors, the real can design is usually different from the mathematical optimum. Our sensitivity analysis shows that the optimal shapes change when material costs change. If the ends are more expensive, the can becomes shorter and wider. If the side is more expensive, it becomes taller and thinner. We can also improve the model by considering wall thickness, different materials, and manufacturing costs. In conclusion, calculus helps us find the most cost-efficient can under the ideal conditions. In reality, engineering constraints make the final design more complex. This shows how mathematics can support well engineering design. Thank you.